Hello everybody, this video is going to be the introduction to the kinetics chapter. We will also learn about rate expressions and how to calculate an average rate for a reaction. I like to start this chapter by just describing a little bit of the differences between the thermo chapter and the kinetics chapter. Sometimes people have a tendency to mix these things up, so I like to kind of go through and explain the difference. So for the thermo chapter, we're really looking at the heat and the energy that's involved during a reaction. In kinetics, we're talking about the speed of a reaction. So for thermo, the question that we're often asking ourselves is there enough energy for the reaction to happen? Or is the reaction going to happen? We're comparing that to kinetics, where we're asking ourselves, okay, let's assume that the reaction does happen. If the reaction happens, then how fast is it going to go? So in a thermo chapter, you're kind of asking yes or no type questions. Where in kinetics, you're really already working under the assumption that the reaction is going to take place. So what you're asking yourselves is just, is it fast or slow? One of the things we have a problem with is that people have a tendency to think that if they can't see the reaction happening with their own eyes, then it's not happening. And that's not true. Okay, it's really important that you understand that slow does not mean that the reaction doesn't happen. You can have a reaction that takes place so slowly, you can't perceive it in your personal, time scale. So if you look outside, you're not going to see necessarily a piece of metal rusting before your very eyes. You're not going to see that reddish yellow color sweeping across a piece of metal. But that doesn't mean that the chemical reaction isn't happening. It's just really slow. So sometimes it helps people to think about the information on the previous slide in kind of a flowchart setup. So the first question you ask yourselves is, does the reaction happen? And that's the yes or no part. That's the thermo part. Then if and only if the reaction happens, then you start asking yourself, was it fast or slow? And that's where the kinetics comes in. There is a time in which the thermo kind of turns into the kinetics. And what I mean by that is there's a specific graph that we looked at in the thermo chapter. The reaction diagrams, remember? Where we were looking to see if it was endo or exothermic. We could see the activation energy peak, things like that. Well, the thermo chapter and the kinetics chapter kind of meet together on these graphs. So I'm going to use kind of cartoon versions with a little car trying to drive up these activation energy bumps, okay? So if you look, this has a really big activation energy, right? Saying it has a lot of energy is a thermo type of a question, right? We're talking about the energy, a lot of energy. This one only needs a little bit of energy to go over the bump because it's much smaller. But this turns into kinetics because if you think about it, if you need more energy to get the reaction started, it's going to take time for you to give the reaction that energy, right? And so that's going to be a slower process. It's going to take this car longer to get over that peak. This one is going to be able to get over that peak very quickly because it doesn't need a lot of energy to be given to it, right? So we kind of have this place where we say the thermo turns into the kinetics. You can answer the question from a thermodynamic standpoint, but that's going to kind of give you the explanation for the kinetics. So kind of moving on, the next concepts to talk about are what we call collision theory, which is literally saying that in order for reactants to undergo their chemical reaction, they have to actually collide with each other. It's really important that you understand that they have to collide hard enough and they have to collide in the right orientation. Activation energy, the big peak that we saw on the previous slide, is the minimum amount of energy those particles need in order for them to react once they collide. So this is kind of where our thermo is, turning into our kinetics, right? Where we have energy that we're talking about, but the answer to the energy types of questions are going to explain whether or not it's fast or slow. So big activation energy means it's going to be like a slower reaction, right? Really, really important we understand fast enough and correct orientation. We say it's an effective collision when that happens. If they just lightly bump into each other, or they bump into each other, on the wrong side of the molecule, nothing's going to happen. So they have to hit really hard, and they have to hit in the right orientation. You got to remember that molecules are three-dimensional. When you're in college, you'll take a class called organic chemistry, and in that class, a lot of what you're learning is about how molecules need to collide in specific orientations for the reaction to actually happen, right? If it needs to hit on the left side, but it hits on the right side instead, the reaction may not take place. So you have to have energy put in to speed the molecules up and to turn them the direction that they need to be. There are ways you can speed up your reaction. You will either be changing how things collide, or you will be trying to lower this activation energy requirement, right? So you'll either be trying to speed things up or trying to lower this activation energy. So let's look at those ways we can achieve those goals. So we could change the temperature. We could change the concentration or the pressure. If it's a gas, we could change the pressure. We could increase the surface area of the molecules, or we can add a catalyst. So if you increase these things, the rate will go up. Now, I have to add the little caveat that, it's typically they would go. If you heat your chemicals up so fast that you start, breaking those molecules apart, you could cause problems, right? You could, in theory, make something so concentrated that, they're getting in the way of each other, right? So as always, we have to kind of realize there's exceptions to everything. But for what we would do in this class, if you raise the temperature, those molecules go faster. So they're going to have more energy when they collide, right? If you increase the concentration, they're going to collide more often because they're able to find, the reactants faster. There's more of them around. Same with surface area. If you think about a sugar cube versus granulated sugar, the granulated sugar is going to dissolve much faster because there's more surface area. And then you may have learned a little bit about catalysts in your biology class. We'll talk a little bit more about those in this lecture. So for a catalyst, kind of what is a catalyst? So a catalyst is a chemical that you're going to add to your reaction, but it is not one of the reactants. It is not directly involved in the reaction, meaning that it's not going to get used up. Your catalyst is present when you start. It helps you do your reaction. You get your new products, and your catalyst is still there at the end. You can reuse a catalyst. You can use them over and over and over again. What a catalyst does is it helps orient your molecule for you. And so it will, turn things in the right direction. Sometimes it will allow the reaction to proceed in a different set of steps, but whatever it's doing for you, it's going to cause you to not have to put in as much energy. And so that lowers the activation energy. It's doing some of the work for you. So if you lower that activation energy, you don't need as much energy, you're going to end up with a faster reaction because those molecules are going to be able to get over that peak easier because the peak has been lowered. EA is activation energy, right? So it's not that you're getting more collisions necessarily. It's not that the catalyst is making the molecules collide more often. It's that when they do collide, they're going to be more effective. And so that will kind of get you to your products at a faster rate. So let me show you one of those activation diagrams. This is showing you with a catalyst and without. So the black line is without a catalyst. Look at all that energy you would need to get over the peak. Compare that to one with the catalyst added, and you can see that it's a much lower peak. You'll need less energy to get over the curve, less energy required when those things collide. You'll have a faster reaction. You'll have more effective collisions taking place. Here's another graph that sometimes people like. I think it does a good job showing you what I mean by more effective collisions. It's a distribution graph. So we have energy and the number of collisions. So you would kind of take the area under this curve to see how many collisions are taking place. Don't worry, that's calculus. We're not doing that here. We're just looking at the pretty little pictures, okay? We don't have to worry about the math. So if you look at the blue one over here, there's so much energy required to have a successful, effective collision that we're pretty far to the right where you see this vertical line. Anything above this has enough energy for the reaction to actually occur. They are effective collisions. When you add the catalyst, look what happens. Your activation energy point is now lower. So anything past that is now an effective collision. And can you see how many more collisions will be effective? Look how much more area under this curve is filled in, right? Way more quantity of good collisions taking place over here. We have more effective collisions. Okay. Next, we're going to talk about what's called reaction mechanisms. So we're not going to do a ton with this. Once again, or the class in college called organic chemistry is where you talk a lot about this. But we need to really understand that the balanced chemical reaction that we write on our paper is like going from point A to Z. It is not necessarily telling us how we got from point A to Z. You don't know if that reaction happened in 1 step or 2 steps or 25 steps, okay? So the chemical equation that we're used to writing is just a summary. Starting and ending point, it tells you nothing about the journey in between, right? The reaction mechanism is the individual baby steps that had to occur for the overall reaction to have taken place. There's no way that I expect you to know what steps would take place, how many steps, how they would happen, none of that. That's that college class again. You can see up here, this is an example of a mechanism. We do what's called arrow pushing or electron pushing, where we're literally showing people where the electrons have to move in a stepwise manner, every baby step along the way. So just a real quick example. Here, right, there's some electrons on this oxygen. They're going to come in and they're going to grab that hydrogen and take it away, right? The electrons that are in this bond here are going to get pushed onto the oxygen here. Now the electrons are on this oxygen. Well, they're going to swing down here and make a double bond. But that means this double bond has to move over here, right? Or it wouldn't work. Well, then that was in the way. So what ends up happening is they just end up on this carbon instead. So now there's these extra electrons here that kind of don't really want to be there. So they're going to reach out and grab onto something else. So now you can see that this carbon's going to get attached to this other molecule. And then the electrons from this double bond get pushed onto that oxygen, right? And the reaction just keeps going. And by the time you're all done, this is what you're ending with, right? but there were a lot of steps in between, and they were complicated steps, and they're not steps that show up when we write our balanced reaction. So it's important that you understand that the reaction has lots of steps. Some steps might be really fast. Some steps might be slow. And so what we look for in kinetics is often what we call the rate determining step. Which of all those baby steps was the slowest? Because the slowest step is the one that's going to dictate the entire overall speed of the reaction. You can only go as fast as your slowest step. If you think about this as an assembly line, I think that's very helpful. You might be making your parts, really, really, really fast, but if the person ahead of you is slow, you are slowed down because of them, aren't you? They are determining how fast the entire assembly line goes. Whoever is the slowest person is the one that's dictating the speed, right? So when we look at our activation graphs, you may see graphs that have multiple peaks because there's multiple steps. Each step has its own activation energy. So in this graph, you can see, well, the first step here is pretty big. This step is smaller. So what that tells me is that the first step in my mechanism is the slow step. I can only go as fast as this one lets me go, right? Once you've gotten over that peak, the rest is smooth sailing, right? Not going to slow anything down. This is what we call the rate determining step. A lot of kinetics experiments are about figuring out what's that rate determining step, because that can help you figure out what the mechanism is. And that's often what we're really interested in. All right. Let's start to transition this from some of these concepts into the calculations. So I'm going to compare how we would write a rate for a car to how we would write a reaction rate for a kinetics chapter, because we are very familiar with rates when we think about driving in a car. So in a car, we're talking about miles per hour, right? If I asked you to turn that into an equation, you may have to stop and think for a minute. Well, if you were trying to calculate your miles per hour and you couldn't see the speedometer, you didn't know how fast you were going, you had to calculate it. What you would do is you would figure out how many miles you drove, and you would divide it by the time it took you. So the equation that you're using is the change in distance over the change in time. And what that's telling you is the speed, right? It's not telling you the energy it took. It's not telling you how you drove there, what route you took. All you're looking at is the speed. For kinetics, instead of miles per hour, we're going to use molarity, the change in concentration over time. Most of the time it's seconds. In theory, it could be something else, but most reactions are pretty fast, so we tend to use seconds. Some reactions are super fast, so we might use milliseconds or something like that. And once again, this is not telling you anything about the energy, right? This is not telling you if it's endothermic or exothermic. It's not telling you how many steps it took you to get there. It's not telling you that pathway, right? All it's talking about is the speed. One thing that we have to be a bit careful of in this chapter is our positive and negative signs. They get a little confusing because sometimes they're implied, they're not told to you. Sometimes you have to give a positive or negative symbol, sometimes you don't. Sometimes you give it to people in words, not the algebraic symbol. So the plus and minuses can get a bit tricky. So the fundamental thing to think about is that if we're using up our reactants, we're going to have a decrease in molecules. So our delta concentration will be negative. So it's going to look like it's a negative rate. If we're making products, our delta concentration will be positive, won't it? So we'll have a positive rate. When you start to get overwhelmed by double negatives and people, using words like increasing and decreasing instead of plus and minus, just go back to this very basic concept. Remind yourself of the basics here, that we're using up reactants. They're decreasing. Our products are increasing. Let's look at this on a graph. So we have the equation up here at the top. We have a line for each of the chemicals involved. One of them is a reactant, two of them are products. You should instantly notice something about those slopes. There's a pretty big difference. Well, the NO2 slope is negative, right? It's decreasing. Because that was a reactant, we're using it up, you can see that we have this negative slope. Since dealing with negatives is often not super helpful, and sometimes it's pretty tough to measure the disappearance of a reactant in the lab, sometimes it's easier to measure how fast something else appears. So I could express my rate based on whichever chemical is most convenient to me. Oxygen is really easy, to collect. Sometimes that might be nice. Sometimes certain chemicals turn colors, so you could measure them with, equipment that can detect the color. Sometimes it's a precipitate that you could weigh or something. There's different practical reasons why you would pick one versus the other. Another thing you should notice is, if you look here, the blue line has a much steeper slope than the red one, doesn't it? And that's because the slopes of these lines are what we call stoichiometrically proportional. This is twice this one, isn't it? I drew the little dotted lines to maybe help you see that. And if you think about it, if you look at the stoichiometry up here, look at your coefficients, you're going to make the nitrogen monoxide twice as fast as you're making the oxygen, aren't you? You're making two of these and one of these at a time. So that's why this one is a steeper rate. That's why it's twice as much, because you're making twice as much. So you have to take the coefficients into account. Every second that we're making an oxygen molecule, we've made two nitrogen monoxides. So your slope should reflect that. All right, next let's do calculating the average rate. So the problem with reactions is that rates are not always constant. It's not always going at exactly the same speed. And if you think about it like we're driving in our car. If I'm trying to go from here to work, I don't always drive exactly 35 miles an hour at every single moment of the entire drive, right? I slow down when I get to things like a stop sign or a stoplight, or maybe I hit some traffic. Maybe once I get on the freeway, I can drive a little bit faster. So the rate's not going to be exactly the same at every moment, okay? So what that means is it's really annoying and hard to measure. So sometimes what we're going to do is we're just kind of going to be lazy, and we're just going to calculate the overall average rate for the entire thing, or for a specific period of time. So that can be way easier to calculate. Here's kind of the generic equation for it: the change in concentration over the change in time. Remember that we always do final minus initial. You would be getting these numbers either from a word problem, maybe it tells you the data in a chart, maybe it's data you collected in a lab, or maybe it's from a graph, okay? But you're somehow going to find a final value and an initial value. So let's do a practice problem. In an experiment, the concentration of substance D was measured at different times. Determine the average rate between 3 and 7 seconds. So I don't care about the entire course of the reaction. I'm only interested in this very specific window of time. Here's your data. Try to find the change in concentration over the change in time for the window of time that we're interested in. You can pause the video if you need a moment to do that. All right, so if I look, my ending concentration was 0.36 minus my starting concentration for the window of time I was interested in, which was 0.47. I'm going to divide that by 7 minus 3. And you're going to notice I get a negative, don't I? So that's going to tell you something. Was that a reactant or a product? It was a reactant, wasn't it? That negative sign mathematically told us that information. Here's the problem. You will probably have a question, like on a quiz, for example, that asks you to calculate the rate. And all your answer choices would be positive. And then everybody kind of freaks out. And it's because you have to be careful, because sometimes the question is going to say something like, what is the rate of disappearance? Putting that word disappearance there is supplying the negative sign for you. You don't have to put the algebraic symbol in that case. So sometimes we're going to put the negative and sometimes we don't have to. It's just kind of, context. It takes a little bit of practice getting used to when is it necessary, when is it not. All right. So now we're going to move on to something that I think is one of the weirder things to try to explain until you get a couple practice problems in. And then I think it's not too bad. But if you're not careful, there's a very common mistake that we tend to make, okay? So sometimes we want to be comparing the rate of one chemical to the rate of the other to the rate of the overall reaction as a whole. And we can get a little confused in our heads about if we're talking about the rate of disappearance of a reactant, the rate of appearance of a product, or the what we call overall rate of the reaction. So let's walk through some examples here. We're going to look at the ratio of these things to each other. Well, the orange to the green, let's do that to make it easier to say, right? So the orange one compared to the green one is a 1-to-1 ratio, right? Every time I use up one of these, I make one of these. So the rate of disappearance is the same as the rate of appearance, isn't it? They're completely related, directly related, but the negative sign has to be dealt with. If you remember when we did calorimetry problems, when we had Q equals negative Q, and the negative sign was making sure that we ended up with double negatives so everything equaled correctly, we're going to have the same thing here, okay? The rate of the reaction is going to be the change in concentration over time, but this one has a negative in front because it was the reactant. This is the product. This will be a positive number. If I put in my rate here as a reactant, it's disappearing, it's negative, I'm going to have negative times a negative, which will equal a positive, which is what I want because I'm trying to make it equal to this thing over here. We have a tendency to like putting our reaction rates in a positive term. And so this is where you're going to start seeing double negatives so that mathematically we get nice positive numbers, which we like to work with. Okay? So what if it's not a 1-to-1 ratio? Well, if it's not a 1-to-1 ratio, we are going to have to take into account those coefficients. So for every one hydrogen that reacts, I'm going to make 2 of these, aren't I? So I can either say that this rate is double the hydrogen, or I could say that the hydrogen disappears at half the rate of the hydrogen iodide. We always like things to be as small as possible. We don't want to talk about something being double. We're going to talk about the other one being half, okay? So what we're going to do is we're going to write out our delta over delta, just like before, delta concentration over delta T, but we're going to divide by the 2 over here so that we're shrinking things down so that they equal each other. This is telling me that the hydrogen disappears at half the rate that this is appearing. You always divide by your coefficients. You don't multiply or you're going to go the wrong direction. Okay? Remember, those reactants are negative, so when you get your negative symbol here, everything works itself out. Okay? This right here, this expression that we've written, is literally called a rate expression. Okay? It's kind of like the writing out the equation that we could use, basically. So, if we want to write the rate expression for this reaction, the nitrogen part will be negative, the hydrogen part will be negative, our products will be positive. I'm going to divide the hydrogen by 3, right? And I'm going to divide over here by 2. So this is what it's going to look like. It looks kind of overwhelming, but take it piece by piece. Negative because it's a reactant. Negative because it's a reactant. Positive because it's a product. Change in concentration over time. Change in concentration over time. Divided by the coefficient so that I can set it equal to the other piece over here. Change in concentration over change in time, divided by the coefficient so that I can set it equal to this one over here. I'm shrinking everything down, okay? This whole thing is what we call our rate expression. I'm hoping you notice that I'm telling you over and over about these double negatives and which things are negative and which things are positive. The semantics in this get really tough for people. They get really bogged down in why we say things one way sometimes and some things a different way, a different time. And a lot of it is just tradition. A lot of it is just trying to make our math easier. A lot of it's trying to get rid of negative signs because we hate them, right? So it's just something you got to get comfortable with, okay? All right, here is the general, generic, using A's and B's example. Okay, if this is your generic expression, right, you can see that we put negatives for what the reactants were. These products are positive. Every piece of my expression is a change in concentration over a change in time. And they're all being divided by their corresponding coefficients, right? So that they all actually equal each other. This is super important because I have to be able to use whichever chemical, I have to be able to measure whichever chemical is going to make my life easiest. Maybe molecule A is hot pink. And as the reaction proceeds, it's going to get more and more and more clear. So maybe measuring the rate at which the bright hot pink compound is disappearing is really easy. Maybe molecule C is a gas. and I can collect it as we go. And it's really easy to measure how much is being made as the reaction proceeds. So I want to be able to do my math with whichever chemical will make my life easier. That's why we need an expression that can all be set equal to each other. All right. Next, what we're going to do is we're going to practice using these rate expressions. We're going to practice figuring out the rate based on one chemical, comparing that to the rate of the overall reaction right over here. So take a moment and write this rate expression down. There's 3 chemicals. Your rate expression should have 3 pieces. Pause the video if you need a moment. All right, so this will be negative. These will be positive. They're all going to have delta concentration over delta time. This one will be divided by 2. This one will be divided by 2. This would be divided by 1, so we don't really put it, right? So here is your rate expression. This will allow you to calculate the rate of reaction based on any chemical. It will also allow you to calculate the rate of disappearance or the rate of appearance for an individual substance. So you can kind of get whatever you need from this expression. So let's use this expression for a practice problem. So same rate expression. The question is going to say the disappearance of N2O occurs at this rate. What is the rate of nitrogen and oxygen appearance? Now this time I was a little bit nice and I gave you the negative sign over here. Technically I didn't have to. Because I told you it was disappearance, because it's a reactant, you should know to put the negative there yourself. Kind of like in the thermo chapter, right? If it was exothermic, you have to put the negative. Same idea. So we're looking at the disappearance of that, which means we're going to need this piece of the expression. Let's start with the nitrogen. We'll come back and do the oxygen later. So we're going to use these 2 pieces. Because right now we don't care about the oxygen, you can ignore this part. We just need these 2 pieces. We're given a known value. Here's something that's pretty tricky. Here's where this common mistake starts to happen. People will think that this number is this entire section here, and it is not. The rate of disappearance is delta N2O over delta T. This entire circled area of the expression with the 1/2 here, that's the rate of reaction. That's the overall rate reaction, right? This piece of it is what this number is, okay? The rate of this is the disappearance of N2O. So what I'm going to have to do is I'm going to have to plug this number in just for this little tiny piece. I have to still put this part into it like it was an equation. I'm substituting in my number here. So this is what I get. Negative 1/2 times my disappearance rate, right? See, my double negatives will cancel. It's going to equal the other rate expression piece that we're using. And I'm looking for the rate of appearance. I'm not looking for the overall reaction rate. I'm looking for just this piece here. So what do I have to do? Well, I have to solve for it as if this were a variable, if this was an x, right? We're really doing nothing complicated other than solving for a missing variable. It's just that our variable looks confusing. It doesn't look like an x. It looks like this weird red blob, okay? Right? It's delta over delta. So I like to remind people that when you're looking for the rate of a specific chemical, You are solving for the delta over delta part. All the junk on the outside has to get dealt with. You're solving for the little blob here that we circled, okay? So when I'm all done, that is my rate of appearance. And you should notice, well, it was a 1-to-1 ratio, right? I guess 2-to-2, right? So it's also a positive because this was being made. They're appearing at the same, or they have the same rate, but the symbols are opposite because one is being used up and one is being made. Now, the reaction rate would be this entire circled part up here. It would be this entire circled part up here. It'd be this entire piece. It'd be this entire piece, okay? The reaction rate is half of this answer. Do you see how if I plug it into the entire circled part, I get the exact same reaction rate number, no matter if I use the N2O or the N2? It doesn't matter because they are equal to each other. The rates of appearance and disappearance may not be equal, but the reaction rate will be equal. Okay. Now let's do the oxygen part. Same rate expression, same questions, same information given to you. We're still using this expression piece, but now we're going to use the oxygen part. Remember, this number right here is delta over delta. I got to plug it in just like it was a variable. So -1/2 times my disappearance of N2O rate equals the other part of the rate expression. The nice thing is there's no fraction over here to worry about, is there? There's no junk. I'm solving for this whole piece. And we get our answer. You can see the double negatives canceled since this was a product. Now if you look, the rate of reaction was equal to this, or it was equal to this, or it was equal to this. And we just solved for this, didn't we? Well, that number should look quite familiar from the previous slide. Wasn't that the exact same number that we had in the blue box on the earlier slide? Because the reaction rate will always be the same regardless of which chemical you're measuring. The rate of appearance and disappearance may not be equal, but what we call the overall reaction rate will be equal. All right, write the rate expression for this one. There we go. Negative reactants, positive products, delta over delta for every piece, dividing by my coefficients so everything is as reduced as possible and equal to each other. Let's use that expression for this practice problem. The disappearance of N2 occurs at a rate of this. What is the rate of disappearance of H2 and the rate of appearance of NH3? We're going to need these pieces. Remember that this gets plugged right in for delta over delta. We're solving for the big blobby part. And we see that the hydrogen is going to disappear at this rate. Which makes sense because it's getting used up 3 times faster, isn't it? For every 1 nitrogen that gets used up, 3 of these hydrogens get used up. You got to remember, right, that this piece here is the delta over delta. That's what we plugged in over here. This number here is our delta over delta. So what's our reaction rate? Well, our reaction rate would be negative of this number. It would be negative 1/3 of this number. And if you punch those out, you get the same thing, don't you? You should also notice that this results in our reaction rate always being positive. That's what I was talking about, how we're kind of doing some math here to force our final reaction to be positive because we just like thinking of it that way better. All right, now let's do the NH3 part. Same expression. This time we're going to use the NH3 portions. Remember, this is your delta over delta that you plug in. And you're now going to solve for this delta over delta. Right? You're going to isolate the delta over delta like it were a variable. So you find that piece, and that's what you get. Now if we wanted the reaction rate, remember it would be negative of this, like we saw on the other slide. It would be negative 1/3 of this one, which was the same answer. And if you took 1/2 of this answer, you get the same thing, don't you? And they all end up positive for our reaction rate. All right, for the last one, I want you to try to do this one by yourself. I'll click through the slides. I'll kind of prompt you on what to solve for. You pause the video, give it a try, and then I'll just click through the answer and see how it goes. Okay? So write the rate expression for this reaction. Pause if you need some time to do that. All right, we have negative reactants, positive products, deltas over deltas, and dividing by coefficients. Let's use that. They tell us the rate of appearance of our product, and we want to know what the disappearance rates for the reactants are. Start by trying to find the rate of disappearance of oxygen. Do the oxygen first. Go ahead and pause. All right, let's see how it went. We're using all these pieces. This is our delta over delta. So if you notice, I have to put the 1/2 here, don't I? 1/2 delta over delta equals negative 1/3 delta over delta. Solve for your delta over delta pieces, and that's the rate you should have ended up with. Now I'd like you to see what the reaction rate would be. You can either use the number for the iron oxide or you can use the number for the oxygen gas. It doesn't matter because remember you should get the same answer. All right. Well, 1/2 of this number or negative 1/3 of this number. They both give you the same answer. Your reaction rate would be 3.53 times 10 to the minus 2. Okay, now let's do the same thing, but try it for the iron. Same expression, same question, but this time you're using the iron part. Pause and try to figure out what the rate of iron disappearance would be. All right, we're going to have 1/2 of our iron oxide rate equaling negative 1/4 times delta over delta. I'm going to isolate my delta over delta. That's my variable. That's my rate of disappearance. I'm going to move all this junk to the other side. And that's the rate at which the iron disappears. Now, just to double check our reaction rate, plug this into the expression here, right? Plug this number in. Double check that you get the same rate of reaction as you did on the previous slide. Negative 1/4 of this gives you the same answer. Okay. All right, everybody, that's it for this lesson. That was a lot, but there were just some concepts that you learned. The average rate, which was not too bad, right? Just doing a simple average calculation. And then this rate expression stuff. Once you do a couple more of these, I think you'll get pretty good at it pretty fast. All right, everybody, that's it. I hope that was helpful. Bye.